5.4, Factor and solve polynomial equations. In this lesson, we'll take what we know about solving quadratics and use that information to help solve other higher-ordered polynomial functions. Let's start with quadratic factoring review. In each of these expressions, try to figure out what the factors are. Our first example, 8x squared plus 20x. Notice there isn't a constant at the end to multiply a times c. Our plan would be then to look at both terms and see if there's anything that they both have in common. We have an 8 and a 20. The biggest amount for a factor that we could take out of 8 and 20 would be 4. Each term has an x in it, at least, so we can have 4x. That's called a common factor. And that would be part of that breakdown process. Now put a parenthesis after to see what would be left over. In that first term, 8x squared, if we factor out a 4 and an x, 4 goes into 8 twice, and then we'd have an x that's still left over. There's a plus in between. 20x divided by 4x, well, 4 goes into 20 5 times, so there's a 5 left over, and the x cancels out. So we have 4x on the outside times 2x plus 5 on the inside. That's factored. The next one, x squared plus 7x plus 12. So now this is in that standard form for a quadratic function. If the number in front of x squared isn't written, remember we default that to a 1. So if the number out in front is a 1, we go ahead and split that constant at the end. Numbers that multiply to get 12 and add to get 7 at the same time would be 3 and 4. So then we break down our two parentheses, split up the x squared into an x and an x in each one of the parentheses, and then we put the 3 and the 4. And you can write those in either order. To make sure we get positive 12 when we multiply and positive 7 when we add, we'll make both the 3 and the 4 positive. And there's your factored form. Try the next one. X squared minus 8x plus 16. Again, technically the coefficient in front of x squared is 1. Now we want to try to break down 16 in a way to get negative 8 in the middle. Well, 16 breaks down into 1 times 16, 2 times 8, or 4 times 4. So if we use 4 and 4, we'll set up our two parentheses. The x squared separates into x times x, and we'll use 4 and 4. This time now we want positive 16 when we multiply, but negative 8 when we add. That means both of the parentheses will have x minus 4 in them. And you can also write this as x minus 4 squared. Either form would be the factored version for x squared minus 8x plus 16. All right, down below, x squared plus 6. So now we're missing that middle term. X squared plus 0x plus 6. To try to break down 6 and get 0 in the middle, the only thing you can multiply to get 6 would be 1 and 6 or 2 and 3. So if we can't find a factor pair for 6 to get 0 in the middle, this quadratic expression is not factorable. And sometimes that happens when we try to break down into smaller parts. Just not factorable. The next two also have missing middle terms. So x squared minus 9 is the next one. X squared minus 9 would be like saying x squared plus 0x minus 9. We need to try to figure out what numbers multiply to get 9, but then cancel each other out in the middle. Well, 9 could be broken down into 1 times 9 or 3 times 3. And then to get negative 9, if we use the 3 and the 3, like so, to get negative 9 when we multiply, one of them needs to be negative. And then to get 0 when we add, as long as one's positive and one's negative, that would give us both situations. This is called a difference of two perfect squares. And we talked about this factor rule back in chapter 4. Anytime you have a perfect square minus another perfect square, we can factor into a product of smaller parts. For this last example, we have 4 and x squared, so there's a perfect square, and then 25. The 4 is going to split apart into 2 times 2. The x squared will split apart into x times x. And now think about 25. 25 breaks down into 5 and 5. And remember, to get minus 25, one of the 5's needs to be positive and one needs to be negative. And since that middle term is missing, as long as we have one of each sign, they would add together to get 0 if we multiplied. So that again is your difference of 2 perfect squares. To transfer this to higher ordered polynomials, and when you're asked to factor, you literally just want to keep the same kind of idea as quadratics. Write out as a product of unfactorable smaller polynomials. It's often common to check for a common factor first. What we'll take a look at is a variety of different types of higher ordered polynomials. In the first example, we have x to the third power. So now this is an example of a cubic function. We can't do two parentheses until we have a quadratic function. So we have x to the third power plus 2x squared minus 15x. Notice right away you can tell that each of the terms has an x in common. It doesn't appear a number would come out of anything, but we have a variable that matches. If we factor that x to the outside, the first term would then get smaller. It would reduce down to x squared, and now that would be quadratic. The 2x squared in the middle would just come to 2x, and then minus 15 would be our constant. Once we split this up into this product of smaller parts, we can take the quadratic on the inside and follow our quadratic factor rules. What are numbers that multiply to get negative 15 but add to get positive 2? 15 breaks down into 1 times 1 times 15 or 3 times 5. And I think we can work with the 3 and the 5 to get that 2. So I'm going to split that parenthesis into smaller parts. Take the x squared, separate it into x and x. 15 would break down into 5 and 3. We want negative 15, which means one of the numbers needs to be positive and one needs to be negative, and positive 2 when we add. If we make 5 positive and 3 negative, adding them together would give us that 2 in the middle. For the final answer, though, make sure to drop that first variable straight down. So here is your product of unfactorable polynomials. That's the factored form for x cubed plus 2x squared minus 15x. Let's take a look at the example on the right. 2y to the fifth minus 18y to the third. Notice we have a coefficient of 2 and 18. 2 would come out of both of those. We have y to the fifth and y to the third power. The biggest amount of y variables we could take out of both terms would be y to the third power. And now let's see what's left over. If we take 2y to the third out of 2y to the fifth, the 2's would cancel, and if we're dividing the y's, we subtract exponents. That would give us y squared. Minus 2y to the third out of 18y to the third. Well, 2 goes into 18 9 times, and y to the third would just cancel itself out. Now that we've separated into a product of smaller parts, we have y squared minus 9, and that's a difference of 2 perfect squares. That'll always break down. The y squared term will split into y times y, and 9 will split into 3 times 3. In order to cancel out the missing middle term, remember one's positive and one's negative, and you can write them in either order. And then last but not least, drop down that product of 2y cubed times y plus 3 times y minus 3. Another option for factoring a cubic polynomial is called grouping. And grouping works if you can't find a common factor within your set of terms. We have x to the third power minus 3x squared minus 16x plus 48. Oh, wow. If we were to graph this one, it would cross the y-axis at 48. We don't have to do that, thankfully. So we want to figure out how to break this down into a factored form, and we're going to use the method called grouping. So here's how this works. Put parentheses around the first two terms. So it's like you're grouping them together. Although I'm going to redo that second parenthesis so that the 2 is, oh, that's just not getting any better, is it? Well, that's good enough. And then we'll put a parenthesis around the minus 16 plus 48. Taking a look at the terms in the parentheses separately, now look for that common factor. Once you kind of split up the polynomial, I notice in that first parenthesis we have an x cubed and an x squared. We can factor x squared out of both of them. And that would leave us with x and minus 3. Okay, so then in that second term, I want to factor out the negative for sure. We never want a negative lead term in the parenthesis. And then 16x and 48, I think 16 actually goes into both of them. So if we take negative 16 out of negative 16x, we still have x left over. Watch this next part though. If we take negative 16 out of positive 48, that's going to change the sign to subtraction. And 16 goes into 48, oh, guess what? 3 times. The purpose of grouping is to try to find a matching factor in this process. Notice this x minus 3 and this x minus 3 are the same. That means that's one of our actual answers, but just one. And then we take the parts on the outside, the x squared and the minus 16, and we group them together in a separate parenthesis. So x squared minus 16. Our goal is to factor completely. The x minus 3 is factored completely, but x squared minus 16 now can be written as a product of smaller parts. They're both perfect squares again. So we can split apart that x squared into x times x. The 16 would be 4 and 4, and then just make one positive and one negative, and there's your factored form. Drop down that last parenthesis, x minus 3. This cubic polynomial has 3 separate factors, x minus 3, x plus 4, and x minus 4. Before we end the video, I'd like you to write in between this example and the special factoring patterns down below. We're going to add something to our slide. All right, find some space if you would please, and I want you to list the first 10 perfect cube values. We've done a lot of work with perfect squares, but there are special factor rules when you have perfect cube values within your polynomial as well. So if we're going to do 1 through 10 cubed, you can write this out as you go along if you'd like. 1 cubed is 1 times 1 times 1. Well, that's just 1. So 1 is an example of a perfect square and a perfect cube value. 2 to the third power, 2 times 2 is 4, 4 times 2 is 8. That makes 8 a perfect cube value. 3 cubed would be 27. 4 cubed is 64. So 64 is a perfect square and a perfect cube. That's fun. 5 cubed is 125. So we're going to get up to some kind of bigger numbers. 6 cubed is 216. 7 cubed, 343. 8 cubed is 512. 9 cubed is 729. And then 10 cubed is 1,000. We will see these kinds of numbers embedded within our cubic polynomials, and they have some special factoring rules that we will do together in class.